What if I told you that you aren't actually moving through space right now? Like, what if the empty space around you is actually the densest, most rigid structure in the universe?
Right. And to take it a step further, what if you, like your physical body, the device you are listening to this on, the planet itself, are really just a series of glitches, sort of glitching your way through that structure?
I mean, it is a completely wild thought to start off with. But welcome to our deep dives. Today we have a single, incredibly fascinating source for you.
Yeah, we are looking at a theoretical physics paper by David Welker. It's titled Shaking Tangled Dimensions, a Nascent Theory of Everything.
And just to be completely clear right up front, we aren't declaring this the proven ultimate truth of the cosmos, right?
Yeah.
Our mission today is just to explore a radically original, thought-provoking framework.
Definitely. It's a model that tries to unify gravity, quantum mechanics, and particle physics, but it does it without relying on impossibly dense abstract math.
Yeah, it uses a surprisingly physical geometric structure instead.
Yeah.
So, okay, let's unpack this. To even begin to wrap our heads around this, we have to completely discard the traditional idea of empty space, right?
Exactly. We usually treat the cosmos as this passive void, like an empty stage where physics just happens. But in this framework, the stage itself is the active participant. It is quite literally the only physical thing that actually exists.
Okay, so what exactly is this space made of in the theory?
So in the Tangled Dimensions model, or TD for short, space is not a smooth, continuous vacuum at all. It's discrete. It has a fundamental physical limit at the Planck scale.
So it's basically built out of tiny building blocks.
Yes, an infinite lattice of interconnected units that the paper calls cores. And each one of these cores isn't just a simple microscopic box. According to the paper, a single core contains 9 dimensions.
Wait, hold on a second. 9 dimensions? I mean, I can barely picture 3. I've got length, width, and height. Where on earth are you hiding 6 other dimensions inside a microscopic box?
I know, it is definitely a conceptual hurdle. But you have to think of a dimension here not as an alternate universe you could travel to, but more as an independent directional property.
Okay, a directional property, tracking so far.
Right. So inside every single core, you have 3 spatial dimensions, your standard X, Y, and Z. But alongside those, geometrically bound to the exact same central point, you also have 3 electrical dimensions.
Wow, okay. And the other 3?
The last 3 are the dark dimensions, and every single core connects all of its dimensions to the corresponding dimensions of its neighboring cores. This forms a massive quantized cubic lattice.
Okay, so it's not a box containing tiny little universes. It's more like a highly complex intersection of 9 different wires, all knotted together at one microscopic junction.
That is a great way to picture it, yeah.
And if I string enough of those junctions together, I get the universe. It gives me a very specific visual, actually. It's like zooming in on a high-definition digital photograph.
Oh, like looking at the pixels?
Exactly. From far away, it looks like a smooth, continuous image of a face or a landscape to you. But if you zoom in close enough, eventually the smoothness just breaks down and you see the individual square pixels. The universe, in this model, is similarly pixelated.
Right, that analogy maps perfectly to the TD model.
But if space is made of these multidimensional pixels, how does anything actually happen or move within them? Like if I throw a baseball or a bunch of cores physically flying through the lattice.
Well, what's fascinating here is that no physical cores are ever moving from point A to point B. The cores themselves are entirely stationary relative to the lattice.
Wait, really? So nothing actually moves?
Not physically, no. Motion in the TD model is entirely about changes in the angles or the tangles between the dimensions of neighboring cores.
So the baseball isn't a solid object plowing through blocks of space. The state of the blocks is just updating, passing the geometric pattern of the baseball down the line.
That is the logical conclusion. Imagine a stadium wave. The people aren't running around the perimeter of the stadium, right? They are simply standing up and sitting down in sequence.
Ah, okay. The wave moves, but the medium remains in place.
Exactly. When a force is applied in this model, the dimensions within a core tilt. They change their angle relative to a central reference point, which the paper calls C.
And then what happens to the core next to it?
That angle change forces the neighboring core to adjust its own angles to compensate, and then that geometric shift propagates through the entire lattice. That sequential propagation is what we perceive as motion.
That is just wild. But if these cores are constantly updating their angles and passing these geometric shifts along, it feels like we were talking about a mechanical machine.
Very much so. It's highly mechanical.
And if motion is just updating angles, what happens when things get really dense? Because this dynamic process leads us directly to a mind-bending redefinition of gravity, doesn't it? Gravity isn't a pulling force here.
It is absolutely not a pulling force. To understand gravity in this model, we have to look at how these spatial dimensions interact when they undergo that tilting process we just talked about.
Okay, so what happens when they tilt?
Well, in flat space, meaning zero gravity, zero acceleration, the spatial dimensions of adjacent cores are perfectly perpendicular to that central point, C. They barely interact, they only touch at their absolute boundaries.
There's the outer borders of our pixels brushing against each other, basically.
Correct. But when you introduce mass, the spatial dimensions in that localized area tilt inward towards C. And because these dimensions have a physical thickness, a real physical volume, this tilting causes the spatial dimensions of neighboring cores to jut into one another.
So they actually overlap.
Yes, they overlap heavily. Gravity is directly determined by the volume of this spatial overlap.
So the steeper the tilt, the more the dimensions overlap, and the stronger the gravitational effect you feel.
Precisely. And that mechanism has a hard geometric limit. If the spatial dimensions tilt so much that they overlap completely, like 100%, you hit the maximum possible density for a core.
Which would be a Planck density, right?
Exactly. A massive region of completely overlapping cores is what this model calls a black hole. It's not a singularity of infinite density where math just breaks down.
It's simply a region where the spatial overlap is completely maxed out. Okay, here's where it gets really interesting to me. Because the paper links this physical overlap directly to the flow of time.
Yes, it does.
It makes me think of a computer processor rendering a video game. Like when your character is just staring at a blank sky, the processor handles it easily. The game runs fast.
Because there's very little data to update.
Right. But when you walk into a dense, complex scene with explosions, lighting effects, 1,000 moving pieces, the computer has to work much harder to calculate all that overlapping geometry. The frame rate drops, everything slows down.
It bogs down completely.
So is this basically why time slows down near a black hole? Because the processor of the universe literally takes longer to update those heavily overlapping cores.
That processor analogy maps beautifully to the math of the TD framework. Time isn't an independent flowing river here. It is fundamentally tied to the local update dynamics of the lattice.
So there's actually a frame rate to reality.
Basically, yeah. The smallest theoretical unit of time, the Planck time, is essentially the tick or the update interval of the universe. During each tick, the cores compare and adjust their angles with their neighbors.
And if they're overlapping heavily,
when the spatial dimensions are heavily overlapping, like in a deep gravitational well updating, that larger shared volume is physically less computationally efficient. It requires more ticks to process the geometric changes.
so time literally moves slower for that area.
Exactly. It is a purely geometric cause for time dilation. To an outside observer in flat space, the clocks in that dense, overlapping region are ticking slower because the lattice physically takes longer to untangle and update those specific cores.
That is incredible.
You can even observe this mechanically with light. If a photon travels down into a gravitational well, its leading edge hits that dense overlap region before its trailing edge does.
Oh, wow. So the front part slows down first.
Right. The front bogs down while the back is still moving at normal speed. That causes the photon's wavelength to compress and its energy to spike. There is no mysterious gravitational pull at all. It's just a purely mechanical traffic jam.
Okay, my mind is thoroughly expanded on space and time right now.
Yeah.
But if the background grid of space and time is just overlapping cores, what is the actual physical stuff? Like, what am I made of? What is the light hitting my eyes made of?
This brings us to the second set of dimensions inside every core, the 3 electrical dimensions.
Because you said earlier we aren't actors on a stage. We are made of the stage itself.
Exactly. And to picture this, we actually have to go back to the very beginning. Before the universe began, before time zero, the paper suggests all these dimensions were entirely disconnected and unaligned.
Just floating randomly.
Pretty much. But when the Big Bang happened, they violently snapped together into this lattice structure, trying to achieve perfect symmetrical alignment. But the snap wasn't perfect.
Ah, it's like zipping up a jacket too fast and missing a tooth.
Yeah.
You get a bubble in the zipper that you can't get rid of.
That is a perfect way to visualize it. Residual misalignments remained permanently trapped in the electrical dimensions. The paper refers to these localized misalignments as kinks.
Kinks, okay.
Yeah. So a fundamental particle is not a tiny billiard ball floating inside a core. A particle is the localized kink. It's a twist or a geometric misconnection in the electrical dimensions of the lattice itself.
So an electron isn't an independent object at all. It's a specific type of knot in the wire of the universe.
That's the exact mechanism. An electron is defined as a core where all three of its electrical dimensions have a negative kink.
And that creates mass.
Yeah, that specific geometric imbalance distorts the surrounding spatial dimensions as well, which is what creates the effect we measure as mass. Up and down quarks, the fundamental building blocks that make up the protons and neutrons in your body, are simply different combinations of positive and negative kinks distributed across those three electrical dimensions.
So what does this all mean for something like light? Because we've been taught for decades about wave-particle duality, right? Does this mean light isn't a wave or a particle, but literally a physical glitch traveling down a wire?
It radically redefines light. A photon is modeled as an extended structure made of two kinks, one positive and one negative, chasing each other at the speed of light through the electrical dimensions.
Wait, chasing each other?
Yeah, it's not a dimensionless, point-like particle. The energy of the light is simply determined by the physical distance between these two traveling kinks. If they are closer together, you have higher energy, like blue light or X-rays.
And further apart?
Further apart means lower energy, like red light or radio waves.
And because it's two kinks traveling together in a paired structure, their relative orientation to each other gives us polarization. If they are parallel, it's linear polarization. That is beautifully mechanical.
It really is. Everything has a geometric reason.
But what about quantum spin? I have always been deeply confused by the explanation that quantum particles have spin, but they aren't actually physically spinning like a top. And then there's superposition, where a particle's spin is supposedly pointing up and down at the exact same time until you look at it. Does this theory fix that headache?
Yes. The TD model completely discards that quantum mysticism. It argues that spin is not an intrinsic magical property of a particle, it's an emergent geometric effect.
How so?
Imagine the electric field of an electron. Naturally, it wants to radiate outward in a perfectly spherical shape.
Right.
But remember the structure of our lattice?
It's cubic. It is a rigid, pixelated grid.
Right, so you're trying to force a perfectly round peg
Into a purely cubic hole.
and it doesn't fit seamlessly. Because of this fundamental geometric mismatch, the electrical dimensions of the core surrounding the electron are forced to constantly update and rotate to maintain an approximation of this spherical shape.
Oh, wow.
Yeah, so spin is simply this wave of rotational updates endlessly circling the core. Now, when you apply a strong magnetic field to this system, these rotating electrical dimensions are forced to align with it.
But they are trapped in a grid.
Exactly. Because they are locked within a rigid cubic lattice framework, there are only two stable geometric configurations where they can align and continue to rotate smoothly without breaking the grid.
Binary. Up or down.
Mm-hmm.
No superposition required at all. It just physically can only click into one of two slots because the grid won't allow a diagonal rotation.
It explains the binary nature of quantum spin purely through geometry. It completely bypasses the need for a particle to exist in two contradictory states at once.
That makes so much more sense than a magical particle being everywhere at once.
It also elegantly demystifies the famous double-slit experiment. The lattice itself guides the moving kinks. As the kinks travel toward the slits, the wave-like perturbations in the lattice guide their path.
Sort of like surfing a wave.
Pretty much. It operates very similarly to the pilot wave in Bohmian mechanics, but there is no invisible, ethereal guiding field. The physical geometry of the space itself is the guide.
Okay, let's follow that logic for a second. If the lattice provides this incredibly structured mechanical geometric guidance, why is the quantum world famous for being completely chaotic and unpredictable?
That's the big question.
Right. I mean, we have Heisenberg's uncertainty principle telling us we can't know everything at once. We have particles supposedly popping in and out of existence. How does that chaotic reality work if everything is just rigid pixels and geometric kinks?
This is where we introduce the shaking part of the paper's title, Shaking Tangled Dimensions. The lattice is not perfectly rigid and still. It is constantly oscillating, vibrating violently at the Planck-scale.
Wait, why is it vibrating? What's actually shaking the stage?
It is a combination of immense cosmic forces. You have cosmic background noise, gravitational waves constantly rippling through, and, most importantly, residual energy left over from the violent snap of the Big Bang itself.
So the whole universe is just jittering.
Yeah, think of it as a persistent underlying quantum foam. Because the entire lattice is constantly shifting and jiggling, conserved quantities like energy and angular momentum have to constantly be micro-adjusted across the dimensions just to stay balanced.
Wait, let me see if I'm getting this. So
That-
the universe is actually deterministic and mechanical, the bottom layer, but it's just vibrating so much that it looks random to our instruments.
That's the idea, yes.
It's like, imagine I give you a highly precise ruler and ask you to measure the exact length of a piece of string on a table. You do perfectly. But now imagine you have to do it while I am aggressively shaking the table.
You're going to get a slightly different measurement every single time.
Right. Not because the string is magically changing length in a state of superposition,
Yeah.
but because the environment itself is chaotic.
If we connect this to the bigger picture, this is one of the most profound insights in the paper. The author explicitly links this shaking to a concept called Baranday's stochastic quantum correspondence.
Stochastic quantum correspondence.
Basically, Baranday's demonstrated mathematically that you can generate quantum mechanics-style probabilities from a purely classical system, provided that system contains an underlying indivisible randomness.
And the shaking lattice provides that exact randomness.
Exactly. It provides the actual physical mechanism for it. It removes the philosophical idea that the universe is fundamentally a puzzle or magical. The uncertainty is just an emergent statistical imprint of a violently vibrating physical reality.
Man, it really takes the spooky out of spooky action at a distance, too.
Yeah.
Like if two particles are entangled, they don't have a telepathic connection. They're just physically linked by the dimensional couplings in the continuous lattice. They literally share the same shakes.
The correlation is pre-encoded in the continuous geometry of the space between them. There is no faster-than-light communication. The lattice itself maintains the balance.
Okay, let me just pause here and make sure I have all of this straight, ensuring you listening at home are tracking with us before we add anything else. We started with empty space, but it's actually a grid of microscopic cores.
Right.
Gravity is just the spatial parts of those cores overlapping and lagging the universe's frame rate. Matter and light are just twisted kinks in the electrical parts of those cores. And the whole thing is vibrating so violently that it makes the microscopic world look blurry and random to our lab equipment.
That is a remarkably succinct synthesis of the paradigm so far.
Okay, good. Because I haven't forgotten about those 3 dark dimensions you mentioned at the very beginning of the deep dive. We've used the spatial ones for gravity. We've used the electrical ones for matter and light. What on earth is happening in the dark dimensions?
Well, just as you can have localized kinks in the electrical dimensions, which create the normal matter and light we interact with every day, you can have kinks trapped in the dark dimensions.
Oh, interesting.
Yeah, and because they exist in an entirely separate dimensional set within the core, these dark kinks cannot interact with the electrical dimensions at all. They emit no light, they absorb no light, they carry no electrical charge.
But they are still physically inside the core, which means they still take up volume. They still work the spatial dimensions.
That is the key connection. They cause the spatial dimensions to tilt and overlap, creating a gravitational footprint.
Which perfectly describes dark matter. I mean, it has mass, it bends space, it holds galaxies together, but we absolutely cannot see it. But here's my question.
Sure, go for it.
Normal matter clumps together to form stars, planets, and incredibly dense objects. Why doesn't dark matter clump together to form dark stars or dark planets? Why does our telescope data show it existing mostly as this diffuse, ghostly halo around galaxies?
It's a great question.
Is it like a snow globe? Like the dark matter particles or dark kinks want to settle and clump together due to gravity, but the shaking of the lattice we just talked about acts like someone constantly shaking the snow globe, keeping it entirely dispersed.
You are hitting right on the core mechanism there. The paper proposes that the dark dimensions likely possess weak self-organizing tendencies. They do feel the pull of overlapping space.
So they try to clump together.
They do try. However, in our current cosmological epoch, the continual stochastic oscillations, that violent shaking, overpowers those weak tendencies.
So they just get rattled apart.
Exactly. They can clump loosely on a massive scale due to gravity, which forms those huge galactic halos, but the constant shaking prevents them from efficiently cooling and condensing into stable, highly bound structures like stars or planets.
So they're just constantly being jiggled apart before they can build any complex architecture.
Right. The author does note an interesting caveat, though. Perhaps in the far future, as the universe continues to expand and the ambient energy cools further, the shaking might subside enough for complex dark structures to eventually form.
Wow. Dark planets could exist one day.
Theoretically. But for now, they remain a diffuse, gravitationally responsive population of hidden kinks.
This model really does try to tie absolutely everything up in one geometric bow. Does this framework actually manage to explain the nuclear forces too? Like the strong force binding the nucleus together and the weak force causing radiation.
It does, and it maintains that exact same geometric logic. The strong force, the incredibly powerful glue that binds quarks together inside a proton, is reinterpreted as those electrical dimensions desperately seeking equilibrium.
Because they have unbalanced kinks.
Exactly. Because of this imbalance, they are constantly moving around inside the nucleon, furiously exchanging energetic twists, trying to balance out the electrical field in their local cores to reach a net zero state.
But they can never perfectly share the load, right? Because the kinks are discrete.
Exactly. They can never settle. That relentless, furious drive for dimensional balance is what we measure as the strong nuclear force.
And what about the weak force, the one responsible for radioactive decay? How do you get radiation out of a pixelated grid?
The weak force is simply the spatial dimensions violently snapping to flatten out. Imagine a highly unstable radioactive atomic nucleus. It is incredibly dense, meaning the spatial dimensions in that localized area are overlapping to an extreme degree.
It's jammed up.
Right, it becomes geometrically untenable. Eventually, the spatial dimensions abruptly relax, snapping back toward a flatter state to reduce that intense overlap.
So radioactive decay is literally just a localized geometric earthquake inside the lattice.
That's a really great way to picture it. And that violent geometric snap sends a shockwave into the electrical dimensions, momentarily tangling them into a transient, highly unstable structure we call a W boson.
Oh, and that boson just falls apart.
Instantly. It cannot maintain its shape, so it immediately decays into stable kinks, which shoot off through the lattice as the radiation particles we detect in a lab. Every fundamental force we observe is just a different manifestation of these cores constantly trying to balance their internal geometry.
Okay. Let's take a breath and look at the incredible journey we've just been on today. We started with empty space. We completely threw that away and filled it with a vibrating, pixelated lattice of cores, each packed with 9 dimensions.
A lot to process.
Yeah, and we learned that gravity isn't a magical pull. It's just the physical overlap of those spatial dimensions, which creates a traffic jam that slows down time. We found out that particles aren't little spheres. They are kinks and twists in the electrical wires of the universe.
Right, and light is just a geometric glitch traveling the wire.
Exactly. Spin is just a spherical shape fighting a rigid cubic grid. And dark matter is just kinks in the hidden dark dimensions kept from clumping together by the constant quantum shaking of the whole structure.
It is a breathtakingly cohesive vision. It really demonstrates that physics doesn't have to be purely abstract math, completely divorced from a tangible reality.
No, it doesn't.
There might actually be an intuitive, deeply mechanical, geometric reality beneath all the equations we've spent a century writing.
It fundamentally changes how you perceive the world around you. You aren't walking on a stage, you are the D stage. But as we wrap up, we actually haven't touched on the ultimate fate of this lattice.
No, we haven't, and this raises a really important question, and it's perhaps the most provocative thought left unexplored in the entire paper, the expansion of the universe.
Oh, right, because it's a lattice.
Yes. If the universe is a finite lattice of physical cores, why is it expanding? The expansion of space requires the physical addition of brand new cores into our lattice. But creating new space requires energy. Where does that energy actually come from?
That is a very good question.
The paper suggests it comes from light. As photons travel vast distances across the cosmos, they undergo redshift. They lose energy. The author proposes that this lost energy is actually being utilized to introduce new cores into our universe from the outside.
Wait, so the fading light of the universe is actively building more space?
Potentially, yes. And this leaves you with a profound question to mull over long after you finish listening. If new cores are actively being added to our reality, what is the supply?
Oh, wow.
Are we existing inside a cosmic bubble with a finite number of cores waiting to be drawn in, meaning one day the supply runs out and the universe collapses back into a single point? Or is there an infinite ocean of cores pressing in from the outside, meaning our pixelated reality will continue to expand, fueled by the fading light of ancient stars forever?
Man, the next time you look up at the night sky, remember, you aren't just looking at actors on an empty stage. You're looking at the stage itself, vibrating, tangling, and perhaps actively building itself out of the dark. Thanks for joining us on this deep dive into the tangled dimensions. We'll see you next time.